So today I'll be talking about like this overview of the MVAPICH project. I'll introduce you if some of you are not familiar, especially as an MPI library. And we have been working on this project for almost 21 years now. This is the open source project we are continuing. And I'll try to explain some of the designs and also indicate like not only it can help the HPC, but we are trying to build a converged software stack where you can also run your AI workload and also big data workload. Now, this year especially is very significant for the HPC computing. As you know, like we just had the exaflop systems announced with the Frontier at the Oak Ridge National Lab. And of course, the next week is the supercomputing. I'm not sure whether we'll have a new system or not. I don't know. We'll come to know about that on Monday and Tuesday. But the broad idea is that, I mean, we have crossed the exaflop barrier. And if you take a look at the systems, like this is the Oak Ridge system with both like a slingshot interconnect, AMD CPUs and AMD GPUs. Altogether, it has like a 8.73 million cores. Okay, so as the systems are becoming that large, how do you design software or the middleware for these systems? Now, if you take a look at not only this Frontier, but Fugaku, Summit, Lumi, these are all the top systems, you will see that all of these are being designed with commodity computing architectures. What do I mean by that? Broadly, you have commodity processors like a Intel or AMD, high performance interconnects like InfiniBand or Slingshot, accelerators are like from AMD or NVIDIA, and then Intel is coming up. And then you also have the different SSDs, NVMe SSDs, etc. So once you put all these large kind of systems together, not only on the on-premise, but also the cloud, we are seeing a very similar trend. So the broad challenge is how do we design high performance and scalable middleware for these systems while taking advantage of heterogeneous HPC and cloud resources. So when I say heterogeneous, I talked about CPU and GPU. As some of you know, there are some new things are coming up like a DPU, data center processing unit, IPU. In general, different vendors are talking about that XPU. So how do we take advantage of these to design very high performance and scalable middleware? Now, while we take a look at the technology, let's take a look at the workload. I talked about the HPC earlier, but as you know, these days, any particular workflow, people have a lot of people want to use different kinds of computation. Like sometime you may try to do HPC, might be some other time you might try to do a deep learning, machine learning, or even a big data like a Spark or Dask. So in this context, what is happening is we need to design the software stacks, which is kind of provide a convergence for all these different workload environment, and they need to run both on the on-premise system as well as in the cloud. So in this context, and all these software need actually scale up and scale out. That means scale up. That means within the node, if I keep on adding more CPUs, GPUs, DPU, performance should improve. And then if I have more number of nodes, I should also get good performance. And typically, for over last 40 years, MPI library has been able to provide that, both scale up and scale out for HPC workload. So now the question is, can we take the same MPI middleware, not only try to satisfy the HPC, but also try to do it for the deep learning, machine learning, and the big data? So in this context, I'll introduce the MVAPICH MPI library project. If some of you are not familiar, I'll show some performance numbers of this library. Then I'll go into this other project, HiDL, which is a high performance deep learning and machine learning project. And then I'll go into the HiBD, which is high performance big data project. I'll actually try to show some numbers, how you can accelerate Spark with MPI. And also I'll try to show some accelerating data science application with DAS. And while we have been working from the Ohio State University in all from an academic point of view, a lot of people have also been asking over the last several years to really provide commercial support. So I'll also be talking a little bit about that and then conclude. Now, if you take a look at these exascale systems, as I talked about, purely from HPC perspective, MPI has been a dominant programming models. But as these multi-cores and multi-GPUs are coming, people have been exploring MPI plus X. X can be a simple OpenMP, or it can be OpenSCC. and even you can have MPI plus CUDA. So if you take a look at designing this middleware, you will see a lot of these kind of requirements. These are like wish list. We need to provide scalability for tens of millions of processors for point to point. We also need to take care of collective communication, which is very challenging. Different versions like offloading, non-blocking, topology aware. We need to also balance intra-node and inter-node communication. These days, like the latest, let's say AMD Milan, within a single node, we have 128 cores. Very soon, you will see 256,000 cores per node. So how do we take those communication not only outside, but also internally? Okay, so we need to take care of this intra-node and inter-node communication balance. We need to provide support for multi-threading, integrated support for GPUs, fault tolerance, QoS, hybrid programming, virtualization, energy awareness. So all these are hot topics. People have been working on this for many years, and in our group also we have been working on this for last 20 years. Now, just to understand the complexity, if some of you are familiar, like take a look at the MPI standard, it has been evolving. In 1994, MPI 1 was introduced. It had only 128 functions. 2015, MPI 3.1 was introduced, 440 functions. And now, last year, MPI 4 was introduced, 700 plus functions. And of course, all those functions, these are the different classifications between point-to-point, collectives, derived data types, dynamic process management, virtual topology, RMA. So for any time a new networking technology comes, like a CPU, GPU, DPU interconnect, you need to make sure that for each of these functions, we provide not only the correctness, but we also need to deliver the performance. And this is where the different MPI libraries differ. Okay, and so that means as the technology is evolving, like a CPU, CAS, memory hierarchy, GPU, network adapter, switch, network technologies, there is big range of solutions, design space out there. There are many protocols, algorithms, data movement mechanisms, OS calls, fault tolerance. So you need to not only study these, come up with a better designs where people can actually run it on that like a 10 million core systems and get the best performance. So this is where the MVAPICH project role comes in. We started this project in 2000, almost 22 years back. If some of you remember, like a InfiniBand networking technology, it was introduced in October 2000, almost like 22 years back, and nobody knew how to use that technology for HPC. So we were the very first one to have an MPI library, open source MPI library. That time it was called MVAPICH, that is MVAPICH 1. And we actually demonstrated it at Supercomputing O2. Again, just next week will be the supercomputing here. 20 years back, we demonstrated that. And since then, we've been continuously working. I am very proud of my team. The open source project is continuing for 21 years now. And not only we started with InfiniBand, but now it supports all HPC interconnect, Omnipath, Ethernet, IOR, Procky, even AWS EFA, Rockport, Slingshot 10 and 11, Broadcom, Kernel's network, you name any HPC system, we have that solution. And we have been able to do that with delivering good performance, and currently is being used by more than 3,000 organizations in 90 countries, a lot of organizations in China. If you go to MVAPICH website here and look at the users, you will see a lot of companies and organizations, universities using our things. And just from OISU site, we even crossed 1.6 million downloads just from OISU's website, and it's steadily rising. And of course, at the same time, we've been enabling also to empower many of the top 500 clusters all over the world. And in addition to that, our stack is also available in Red Hat, SUSE, SPAC, OpenHPC. We don't keep track of those downloads. Okay, just from our website, we have so much download. And just from this project over the last 20 years, we have published almost 300 plus publications. And the way we work on, of course, we are a academia. So our first objective is to do research. Anytime some new technology comes up, we first do the research. We actually publish those papers. And in 6 to 9 months, we actually take these and to actually go through very production quality software design and then make it available. So within my group, we have almost like 200 servers continuously running QA test. We have a lot of software people, staff engineers working on this. So over the years, this just shows a roadmap. Like every time some new technology has come, new application domain has come, new kind of MPI standard has come, we've been continuously evolving. And we publish this, our experience actually in this paper. You can take a look at it more details if you have time. Now, as you can see, this is like our release time and downloads. We are steadily increasing over the years. Now, if you take a look at the internal things, I mean, this is how we have built. This is like the software architecture. So below here, you see all the different networking technologies. These are the CPU, GPU, DPU architectures. At the top level, we started with MPI interface, then we have provided PGAS interface, hybrid MPI plus X interface. And then through these interfaces, now we are able to not only support HPC, but also deep learning, machine learning, data science, and big data. So I'll talk about that a little bit later. But this is where our innovations lie. I mean, this is where we try to come up with the best communication runtime so that at the top level, you get the best performance and scalability. So let me show you some internal designs to go into details. So just to highlight some of the aspects. And these are, I'll take the numbers from recent releases. So this is like our 2.3 series, that is the stable series. So we made this release in March, and it has support for all the Rockport switch, Clay Slingshot 10, Mellanox Sharp, etc. Now there is a newer version coming, and in fact today you will be seeing a new release coming out later today. But this is the earlier one. This is we have a new 3.0 series, and this actually now supports, in addition to our own design, it also supports UCX and libfabrics. If some of you are familiar, some of the vendors are trying to only provide their interfaces through either UCF or UCX or OFI. So through this, actually now we support Slingshot 11, kernel is OPX, Intel PSM3, so that we are able to address all the other networking technologies. So let's take a look at some sample numbers. So this, I'll start with point-to-point. That's the most common operation, as you know. So this is like the AMD Milan with InfiniBand SDR 200 gigabits per second. This is the intra-node. That means within the node, two cores within the socket talking to each other. And you will see this is the number is like 190 nanoseconds. Okay, so think of like an MPI. We're able to communicate in 190 nanoseconds between two cores within the same sockets. So the MPI level designs have now gone into the nanoseconds level, and one has to be very careful about how you write the code, how you take advantage of those RDMA principles, and that's what we have been able to achieve that. And then of course within the network we provide like a 23.1 gigabytes per second. Bandwidth is around like a 23.5. We saturate the network, and here node to node, this on the AMD system is like around 1.8 microsecond. Now that is the point to point, but over the years, what is happening is there is a significant importance of collectives, and many HPC, and not only HPC, many of these deep learning, machine learning, and workload, they try to use all reduce. They try to use broadcast. They try to use all to all. And as the system sizes increases, you need to actually come up with better and better algorithms to make sure that you are able to deliver those in the best performance with best performance and scalability. So here, these are some numbers. We have done very tight integration with SARP. There's a Mellanox has a SARP, which they call in-network computing. And these numbers are taken from TAC Frontera system. As some of you know, this is the Texas Advanced Computing System. This has the largest open science InfiniBand system, very close to 8,000 nodes. Okay, so this is where we have taken the numbers. And as you can see, based on some simple designs to based on these advanced designs, we can actually reduce the latency for all reduce, barrier, reduce kind of things by factor of like a 5 to 9. So that is for the blocking collectives. But these days, there is a lot of focus on non-blocking collectives. So what do we mean by that? Like the blocking collectives, let's say I'm trying to do all to all. Every process initiates the all to all, but unless all to all finishes, nobody's able to make any progress with the computation. But then what happens, you lose a lot of cycles and your end applications don't scale. So this is where non-blocking collectives was introduced. Now it can actually do the computation, followed by you can do some communication. But while this communication is happening, as you can see, you can continue to do the computation. That is the whole idea. So I initiate non-blocking, but while the non-blocking all-to-all is going on, I can actually do computation based on the previous data from the previous iterations. So if I can do that, then I'll actually get good overlap of computation and communication. Okay. But the question is, who will make this progress? Because sometimes periodically you need to check whether it's the communication is progressing or not. Might be you have sent me some data based on the algorithm. I need to combine my data with that and then send it out. So who will take care of those things? In fact, here I'll try to show some numbers, especially with the DPU technology. You can actually do a lot of better designs here. So the pure, even the CPU-based systems, we have been continuously working on enhancing this non-blocking collective. So here you will see these are called I barrier, IO reduce. And there are two kind of graphs. So this, like the blue is the previous design. This is the latest release. As you can see, we're able to reduce the latency and improve the overlap, because overlap is important. How you design this internally so that the computations can make progress. So same thing happens here also. We are able to reduce the latency and then improve the overlap. Now, for very latest things, if you think of like a Slingshot 11, that is actually the network which is used on the Frontier system, the #1 system in the world. You can see like a MVAPICH can run there with a 2 microsecond latency. This is like a point-to-point, and then bandwidth, we can actually deliver almost like a 24 gigabytes per second, unidirectional, and around 42 gigabytes bidirectional. So those are the kind of the CPU level numbers, but as you know, over the years, a lot of work has taken place with respect to GPU. I'm assuming many of you might have heard of this terminology called CUDA aware or GPU aware MPI. In fact, almost 11 years back, we actually introduced from my group, we had a paper at ISC 11. We introduced this term, and nowadays over the last 11 years, this has become very popular across all the different MPI libraries, middlewares and all. So what does that mean? So if you take a look at, if you would have done some CUDA level programming or GPU programming, this is the GPU, this is the network. Of course, for computation, I have to offload a kernel, do the computation, but how do I do the communication? So most of the time, people do a CUDA mem copy to the host memory, then do an MPI send, you do an MPI receive, and then you do a CUDA mem copy. So as you can see, if I want to send a very large amount of data, I go through 3 levels of copies, and you lose the performance. So this is where we worked in 2010-11. We worked with NVIDIA, and we also worked with Mellanox. And NVIDIA has introduced called GPU Direct RDMA. That means if the GPU and the InfiniBand are on the same PCI slot, I can actually send data back and forth. It doesn't have to go to the memory. So we introduced this concept that at this side in the GPU, you can device buffer, the send device buffer you can specify, and then you say on the MPI side from the left, you can say, okay, I'm sending, and then the receive side, you say I'm receiving. So then that actually becomes like a, after this, you can see MPI library takes care of everything. Okay, you don't need to take care of anything else. And in that case, we can actually get good high performance and high productivity. So in fact, since 2011, this mechanism has been used. And nowadays, if you use the MVAPICH2 library or any other MPI library, you get very close to the InfiniBand network performance. Like with MVAPICH2 now on any platform, you can actually do a GPU to GPU on a different node in 1.8 microsecond. Okay, like an InfiniBand node to node on the basic CPU is around 1 microsecond. In another 800 nanosecond, you can actually send the data from GPU to GPU. So this is very powerful and is being used now in all different MPI libraries, even Nickel, RICL, all libraries are using that. Now, for the last few years, now we have gone to the next level. Okay, and this is we call on-the-fly compression. Now, even if you use GPU Direct RDMA, let's say if you have a very large data, sending it takes time. But then, especially during the communication, what happens is that the GPU cores are idle. So now the question is, before I send, let's say I have a 4 gigabytes of data to send, before sending it, can I actually use some of the GPU cores to compress and send the compressed data? And then on the receive side, I do the uncompress. Okay. Of course, the compression at the sender and uncompressing on the receiver will take some time. But if I can reduce the size of the message, I'll actually win. And that's what we have done. So this was a paper. It got the best paper finalist at IPDPS 2021. And here we have actually run it on like up to 512 GPU nodes on the Lawrence Livermore Lassen. And this is an actual application, AWP ODC, which is a seismic simulation application. And on application level, we are able to, like, the left-hand side is flops, right-hand side is the second. So higher is better here and lower is better. We are able to push the performance by 35%. 26% here. And this is already available in our latest release. So if you have an application you want to try with compression, just download the thing, install, and turn on the compression flag, and you will see this kind of benefits. Now, similar things we have now trying to extend to the collectives, because collectives level, of course, collectives, if they are designed based on point to point, you will see the benefit. But otherwise, we have actually built in new kinds of algorithms to do the compression. So here it shows like this was presented at ISC earlier. And this is a PSDNS, which is a computational fluid dynamic simulation. Here you can see like we are able to reduce by 30%. And this is a deep speed, the deep learning application. So here you can see we are able to reduce by almost 36%. So there is a very significant role of using this compression. Now, I talked about all these like NVIDIA GPUs, but we have been continuously working on other GPUs, AMD GPUs, and very soon you will see even the Intel GPUs coming up. And here again, this is like we have now the MVAPICH2 library is ROCm aware. ROCm is like their AMD's lower level middleware. So through that, we are able to support. And here you will see, again, within the node, 2 GPUs, we are able to send like a 1.75 microsecond. And as you can see here, we are comparing with our MVAPICH2 GDR with OpenMPI for collectives and all. We are able to give very significant benefits with our design compared to the other libraries. So now let me talk a little bit about DPU, because that is an emerging technology which is coming. So if some of you are not familiar, so the DPU stands for Data Center Processing Unit. So Mellanox / NVIDIA now has introduced these Bluefield 2 adapters, and other vendors are also coming up with similar adapters. So of course, the InfiniBand had this RDMA earlier, but now what they have done, the network adapter has this set of ARM cores. So I call it like executives, which are the CPU, and these are the assistants. Okay, so now the question is, just like in a day-to-day world, executives try to offload things to their assistants, how we can try to do that within MPI libraries. Okay, so I'll start with MPI, and the next section I'll also talk how the deep learning workload also can take advantage of that. So here, especially we have taken the non-blocking collectives. Okay, so that is the focus here. If you remember the non-blocking collectives I introduced. So we have an MVAPICH2 DPU library. This is being done jointly with a commercial startup called Xcal Solutions. So this library is available, MVAPICH2 DPU. So here what we have done, we have offloaded MPI IOL to all, MPI IOL gather, MPI IB cast. And let me show you some numbers. So this is OSU IOL to all. So that is a non-blocking all to all. And especially when you evaluate non-blocking, we also need to make sure that it's not just what is the basic communication latency, but how much it is able to overlap with the computation. Okay, so typically there is a standard benchmark. In fact, in our OSU micro benchmark, which is released together with our MPI library, there are some standard benchmarks which actually initiates the communication, performs the computation, and measures both the computation and communication time. So now if you see, these red bars are basic MVAPICH2, which doesn't have offload capability, but this is the MVAPICH2 DPU. Now you can see like this is a 32 node 16 ppm 512 process. This is 1000 process. We are able to reduce the all to all, which is very expensive, by 22%, 22% kind of things. But then the question is, okay, how about the application? So here we used an P3D FFT. This is an application developed from San Diego Supercomputer Center. And of course, to take advantage of this non-blocking DPU technology, the application also needs to be modified. Okay, this is like a co-designing, because if you just the application is using blocking, we cannot do anything. So we worked with the developers here. They changed the blocking all to all to non-blocking all to all. And with that, now you can see at an application level, we are able to actually give you benefits, 21%, 18%. Okay, so the hardware is the same. Okay, so now if you use an intelligent software like our MVAPICH2 DPU, you should be able to take benefits here. Now, to summarize this part of the talk, of course, I just highlighted only a few things. Of course, this is a 21 years project, continuing. We have a lot of additional features, but this is where you will see the end impact. So these are the numbers from the Summit system, which used to be the number one. As you can see, MVAPICH to library is actually giving far better performance and scalability compared to OpenMPI, UCX, and also Spectrum API. This is from Idaho National Lab. They actually do a lot of nuclear energy research. So they use not only the basic MPI library, on top of that moves, Betsy, libmess, etc. And interestingly, they have actually this slide, I'll show it to you. This was just presented in our annual MVAPICH user group conference we do in August. So until last year, their users were using all different libraries. So these are like their statistics actually. And this is of course the log scale. And now you see this year, 2022, everybody has moved to MVAPICH to library because we are able to really deliver the good features and scalability. And that's how people are moving to our library to really take advantage of all the nice features. Now, very interestingly, I'm also very proud of my team. Many of you must have heard of this NASA's DART mission. The NASA thing went and then caused this, had a hit with the asteroid. In fact, MVAPICH to library actually helped in all these simulations. So we have been working with Lawrence Livermore National Lab, and this project actually started in 2016. 6 years back. So the entire 6 years, they have been using our library to come up with the simulation to exactly predict how the flights will go, how it will actually hit, what will be the impact. So I'm very proud again just to see that we are able to contribute to this kind of a planetary defense solutions. So that is the basic MVAPICH designs. I'll quickly move into the other aspects, the high performance deep learning, machine learning. As many of you know, I mean, the community is heavily using all these TensorFlow, PyTorch, MXNet, etc. And some of you might be knowing there is a lower level middleware called Horovod, Torch Distributed, Deep Speed, etc. So what we have done, we have actually linked our MPI library there. Okay, of course, there are competing library from NVIDIA has Nickel, AMD has Reckel, but since MPI library has already been there, it provides all the solutions. So the question is, why don't we take advantage of those? And that's what we have done. So we have this project called HiDL, high performance deep learning, high performance machine learning. So since we have linked it, if you have installed our library, you should be able to directly run. You don't have to change anything. You exactly run your same TensorFlow, PyTorch applications, but you get the boost in the performance. So please take a look at this IDL. In fact, we'll be making a new release also, might be tomorrow or day after on this. So I'll try to show some two, just kind of an example. One is an AI-driven digital pathology, and then I'll talk about the accelerating deep learning with the DPUs. So here, as I said, like you can use actually our MVAPICH to library to perform all the deep learning application. And deep learning, as you know, we have data parallelism, we have model parallelism. So over the years, what is happening, the data sizes have been increasing. Like you have the pathology, like let's say you are trying to do the pathology whole slide images. So each WSI is like 100,000 pixels. So they cannot fit into a single GPU memory. So they have been always using tiling. But then once you do the tiling, you actually lose the accuracy. So this is where we actually used our like a model parallelism. This was presented at Supercomputing 2020. So what we did, we actually worked with the pathologist, because every hospital, as you know, you get a lot of images. And the question is, can we build deep learning model? And then when a new patient comes or a new image comes, very quickly we'll be able to identify in which class or which disease does it belong to. So in the beginning, they were trying to do this deep learning on one node with one GPU. It was taking 30 hours. But we worked with them like with one student with around 3 months. We were able to reduce to almost like a 0.46 hours. Okay, like a 24 minutes. And we were able to give like a overall reduction in 15x. And then throughput, we were able to improve it again at 22x. So I'm just showing really an end solution here using our approach. Now, the similar kind of designs, I talked about DPU for HPC. Now you can actually use the DPUs for even dual training. You can boost the performance. So if some of you are familiar with the deep learning training, there are multiple steps like a data augmentation, training, model validation. So now the question is, if you think of like that executive and assistants, of course, the ARM cores are running with a reduced speed compared to the host speed. So everything we cannot offload. So the question is, what is the best offloading mechanism? And then we did a lot of analysis here. This paper was presented in the hot interconnect last year. So here we came up with this mechanism where the training process is running on CPU, data augmentation is running on DPU, testing process is running on the DPU. So here again, we have an actually Xscale AI DPU package. It will be actually released just in the next 2-3 days. And this is built on top of our MVAPICH 237 with Horobot 0.25. And now if you see this kind of number, like a training ResNet 20V1 model on the CFAR 10 data set. So again, here you will see like with pure CPU, this is the red line, which is higher. But now if I use offload some of these things to DPU, I get almost like a 16 to 18% benefit. Okay, it is not a big number, but now if you see at an end, deep learning execution time, I mean, it's reducing by 20% is also is significant. Similarly, this is like a training of the ShuffleNet model on the tiny image data sets, and there also we see the same benefits. Now that is the high DL. So then the question is on the high BD. This is a project on the big data, how we can leverage MPI level solutions for the big data. Some of you might be familiar with this high BD project. This again has been running since 2013. So this is like the Hadoop, Spark, Kafka, HBase, Memcached, all those things. We did native designs over InfiniBand. Okay, and of course this is a lot of these stacks are still very widely used by 340 organizations. We have more than like a 44,000 downloads. But now as these newer networks are coming, the question is, do we redesign is everything for every network, or can we leverage the MPI library? Okay, so let me show you both sides of numbers. So this is like a RDMA Spark. This is the traditional design what we have done. This is like running on SDSC Comet, like the high bench page rank. Here you can see this is the standard Apache Spark, and then this is our RDMA based Spark. And as you can see, we can reduce the execution time by 30%, 37%, or 43%. This is on pure InfiniBand. Again, with a better software, you can actually do better performance. But now what we have done, we are trying to link MPI through the Spark. Okay, so if you are familiar with some of the Spark design, here you will see the below has this native transport. So what we have done is we have actually linked. So it has a Java native interface, and this is where we have linked to our MPI library with Java support. So we have actually an MVAPICH to J, which is the Java version of our MPI library. We have brought it there. So now if you see, this is like we call it MPI for Spark. Excuse me. In fact, this will be released actually later today. So these are like the different systems. These are some of the micro benchmarks. We have a Ohio high BD micro benchmark. So these are called OHB. So here you'll see this vanilla Spark. So we are trying to show improvement compared to those. So compared to, of course, the standard Spark will improve. Even compared to our RDMA Spark, we are improving because now the technology is improved. MPI library has been continuously adopting better and better mechanisms. So that is the whole idea. Like we should be able to get portable performance. Okay, if we can leverage the MPI library so that every time a new network comes, we don't have to redesign the entire stack, and automatically you will get the benefits. So this is again another like a SDR 200 gigabit system, very similar things like if you keep on increasing to like a very large data sets, 640 gigabytes, 128 cores, even compared to our RDMA Spark design earlier, we can give you benefits like a factor of 2.8, 3.4, even sometimes 4.8x kind of things. So this is also with the Intel High Bench, very similar trend we see compared to how much time it takes the vanilla Spark, the RDMA Spark. Compared to that, we are able to improve the performance. So please feel free to, once we make the release today, if you have some Spark jobs running over InfiniBand or any of the other network, you should be able to actually utilize our software. Now, while we are focusing on the Spark, as many of you know, there is a lot of focus on the data science also. And this is where a new software stack called Dask people have been starting using. And what we have done is, again, the same philosophy we are trying to use, how we can combine Dask with MPI. So we have a release actually MPI for Dask. And here, if you see some of the benchmarks like CUDF. So this is running on the Cambridge Wilkes 3 systems. And as you can see, like there is a 32 Dask worker here on like using 800 systems. Common solutions, like of course you can run it over TCP, but there is also UCX layer you can run. But now with the MPI layer, as you can see, we are able to reduce this time in a very significant manner, like a 5x improvement over UCX. Here also we are able to improve it by a factor of almost 3 and 2. These are another matrix dot benchmark, very similar story. Like we are able to do like around like a factor of 4 better than UCX. And here you can see we are able to maintain that scalability as we keep on increasing the number of tasks. So these are all the solutions from the OSU side. As I indicated, over the years, people have been asking us a lot of commercial support, just like any other commercial software library. So this is where we establish these Excel solutions. And through these, actually, now we provide supports to many national laboratories, international HPC centers. We take care of optimizations, bug fixes. So just like think of a commercial software. It is based on all MVAPICH 2 library, but we'll be able to take care of your entire system, and all your users should be able to get good benefits. And then through this also, we have been able to add like a value added products. I talked about like the MVAPICH 2 DPU. I didn't get time to talk about Xscale AI, but we have an Xscale AI, and I talked about this Xscale AI DPU. So these are the products are also have additional features, performance optimizations, and also there is a lot of additional tools which are integrated there to provide profiling, introspection support, etc. So with this, let me conclude. As I indicated, the upcoming exascale systems and the cloud actually need to be designed in a holistic manner. HPC, big data, deep learning, machine learning, data science, and especially the new computing continuum, which is like even from edge to the HPC centers. I didn't have time on these. We have actually started a very large project now called Icicle, which is the NSF AI Institute. If you go to icicle.ai, you will see a lot of things there. And I just provided some of these overviews. And since we have already crossed example of systems, people are talking about Jetascale systems. And this is where people will be continuing to work. I just want to highlight this. This is a very nice book, which has been published by MIT Press. All our big data computing work has actually gone to here. So if you are really interested in knowing what is the state of the art things, this is with Professor Jiawi Lu, and then with one of my former students, Dipti. And also, as I indicated, these are like we do an annual MVAPICH user group conference. We just finished in August. These are a lot of testaments of how the MVAPICH library is actually working on real systems. So all the slides and videos of these talks are available. Please feel free to take a look. So with this, I'd like to thank all our sponsors, but more importantly, these are all my heroes, past and current students, staffs. They have worked like 21 years. So always I give a presentation, I salute them for their contributions. And while saying that, I'm continuously looking for newer students, staffs, and software engineers. If both on the OSU side as well as Excel solution side, if you are interested in coming to our group, so that you contribute and your name will be added to the previous slide, okay, few years down the road. With this, let me stop here, and I'll be very happy to take questions. Thank you.
Thank you very much.